Hey, good morning, class, and welcome to lesson 8.3.1. How can I use trig ratios? The objective today is to simplify trig expressions by rewriting in terms of sine and cosine, and then determine special angles for trig ratios from the unit circle. All trigonometric expressions can be written in terms of combinations of sine and cosine. While there are 6 trigonometric ratios, you can actually work with just 2. When simplifying expressions involving trigonometric ratios, it is often, but not always helpful, to express all of the functions in terms of sine and or cosine. Express each of the trigonometric ratios in terms of sine and or cosine. Well, sine is already written for you, so that's done. Remember from our lesson yesterday, cosecant is the same as 1 over the sine of x. And cosine is already done for us. But secant, that was the same as 1 over the cosine of x. Tangent from our work earlier in the year is equal to the sine of x over the cosine of x. And cotangent from our work in our last lesson is actually cosine of x over the sine of x. Using your answers from the previous problem, rewrite each of the following trigonometric expressions. Express your answers as a single trigonometric ratio without fractions. I'm going to do A and D for you, and then you can pause it and you can try your work or luck with B and C. Tangent. Well, that was the same as sine of theta over the cosine of theta. All I'm doing is replacing tangent with some equivalent expression. And the cosine is just the cosine. And what happens here is this is the same as cosine over 1. You can reduce your cosines, and you're left with that single trigonometric ratio without a fraction. I'm left with the sine of theta. So the tangent theta times cosine theta is the same as the sine of theta. What about in D? Let's start out by replacing tangent with sine over cosine. So I have sine of theta in the numerator divided by sine of theta over cosine of theta. I'm going to leave a little space, times cotangent is the cosine of theta over the sine of theta. So we write that sine theta times, I'm going to leave a little space, cosecant is the same as 1 over the sine of theta. Now this first fraction, I'm going to take my numerator, sine theta, and multiply by the reciprocal. So let's write down sine of theta times cosine theta over sine theta. I've just taken this and multiplied my numerator by the reciprocal. Times, I have cosine theta over sine theta times 1 over the sine of theta. Now as I'm looking at this, there's a few things that can cancel. Well, the sine of theta can cancel and the sine of theta can cancel. Now that leaves me with actually cosine times cosine. We're going to call that cosine squared, cosine theta squared over sine of theta squared. Well, if my numerator squared, my denominator squared, then that would be the same as cosine over sine. So cosine theta over sine theta squared, and cosine divided by sine is cotangent theta squared. Now, as mathematicians, we're kind of lazy at times, so we really don't write statements like cosine theta squared, sine of theta squared, or like cotangent of theta squared. We actually write it like this. This would be written as the cosine squared theta divided by the sine squared theta. So forget that stuff. This then would simplify into cosine squared over sine squared. That would be the same as cotangent squared theta, which is the same thing as cotangent theta squared. So now I'd like you to pause this and you try B and C and then come back and check your answers. Okay, welcome back. In part B, we have the cotangent of theta times the secant of theta. Cotangent of theta is the same as cosine over sine. Secant is the same as 1 over cosine. This allows us to cancel the cosines that I've done in red, and we're left with 1 over the sine of theta. That is equivalent to the cosecant of theta. Now in part C, we're starting with the secant of theta divided by the cosecant of theta. In the numerator, the secant of theta is the same as 1 over the cosine. And the cosecant of theta is the same as 1 over the sine. So I'm now going to take my numerator, I'm going to multiply by the reciprocal of the denominator. If I take now 1 over cosine times the sine of theta over 1, I get the sine of theta over cosine theta, which is equivalent to tangent theta. More Pythagorean identities. Hopefully you recall from our work in Algebra 2 and some of our work here in pre-calc that we have this Pythagorean identity, cosine squared x plus sine squared x equaling 1. We're going to take and develop 2 additional identities from this. One day, while working with fundamental Pythagorean identity, Gurpreet exclaimed, "I found another identity that involves different reciprocal trigonometric functions." Skeptical Schuyler responds to Gurpreet's outburst by saying, "No way! How did you do that?" "All I had to do was divide both sides by cosine squared and simplify the expression," replies Gurpreet. So let's do that. Let's divide both sides by cosine squared x and cosine squared x. It doesn't really matter if we use x or theta. So on the left side, this is really then the cosine squared x divided by cosine squared x plus sine squared x divided by cosine squared x equaling 1 over the cosine squared x. Now let's replace these ratios with equivalent values. I'm going to replace cosine squared x over cosine squared x with 1 plus sine squared x over cosine squared x. Well, that's the same as tangent squared x. Equals, and 1 over cosine, 1 over cosine squared x, that's the same as secant squared x. So we have a new property that we just proved. 1 plus tangent squared x equaling secant squared x. Not to be outdone by Gurpreet, Schuyler uses the same strategy but divides by sine squared and is pleased to find yet another identity. So now let's divide both sides by sine squared x that gives us cosine squared x over sine squared x plus sine squared x over sine squared x equaling 1 over sine squared x. In blue here I have cosine squared x over sine squared x. That's the same as cotangent squared x plus, in green, I have sine squared x over sine squared x. That's the same as 1 equals, and in yellow, 1 over sine squared x. That's the same as cosecant squared x. Oops, in yellow. Cosecant squared x. So the new property is cotangent squared x plus 1 equals cosecant squared x. Now we're going to try to use these Pythagorean identities to simplify each of the following trig expressions. But what I'd like you to do first, without looking back, is to write the trig expressions up at the top, the 3 that we just learned. So pause this, see if you can remember those 3, write them up at the top so that we can use them as we work through these problems. Okay, here are the 3 Pythagorean identities that we have. 1 plus tangent squared x equals secant squared x. Cosine squared x plus sine squared x equals 1. Cotangent squared x plus 1 equals cosecant squared x. I want to rewrite these trig expressions. I'm going to do A and C, and then maybe you can try B and D. In part A, secant squared minus 1. Well, if I think about this expression up here, what I really have is a tangent squared equaling, if I subtract 1 from both sides, I have secant squared x minus 1 equaling tangent squared x. So let me erase all of that. So this is really the same as tangent squared x. Now I'm going to try part C. Well, 1 minus the sine squared. Well, if I subtract a sine squared from both sides, that would leave me with cosine squared. So I think this is the same as cosine squared x. And 1 plus tangent squared, we know is equal to secant squared. We'll go times secant squared x. Now secant is the same as 1 over cosine. So I'm going to go cosine squared x times 1 over the cosine squared x. If I think about this in terms of fractions, those cancel. I really have 1 over 1 times 1 over 1, or just 1. Please pause this and you try B and D. Before you do that, let me just give you a quick hint. Here, you're going to want to expand or multiply these together. And down here, replace cotangent with something from here and leave the cosecant squared in there. See what happens. Okay, welcome back. Now, I took the 1 times 1 and just started, you can use a box method to multiply these together. I just multiplied these two terms in my first set of parentheses to the 2 terms in the other set of parentheses. So 1 times 1 is 1. Cosine x times 1 is cosine x. 1 times the negative cosine x is a negative cosine x. And cosine x times a negative cosine x is going to be minus cosine squared. In the middle here, we have a cosine x minus a cosine x. That's 0. So now I'm left with 1 minus cosine squared. And if I look at my expression up here, if I was to subtract that cosine squared from both sides, 1 minus cosine squared is the same as sine squared x. In part D, I replaced cotangent squared of x with cosecant squared of x minus 1. Because if I subtract a 1 from both sides, my cotangent squared x equals cosecant squared x minus 1. Then I still have this minus cosecant squared of x. Cosecant squared x minus 1 minus cosecant squared. Well, the 2 cosecant squareds cancel. We're just left with this negative 1. Now I'm going to do a few more here. And I may pause this and have you try one of them on your own. But things that we need to be keeping in mind as we go through this process is, 1, we want to get things in terms of sine and cosine. We want to write in terms of sine and cosine. Not always, but often. 2, use the properties that we've listed on this or in this lesson. 3. Since looks like we're going to be adding fractions, think of getting common denominators. So in this first problem, looks like everything's in terms of sine and cosine already. Now what I need to do is get a common denominator. So I'm going to multiply this second fraction by the sine of a. Since sine of a is a factor in the first fraction's denominator, I'm going to multiply by a giant 1, which is sine a over sine a. Then in the first fraction, I want to multiply by what's in the denominator of the second fraction. That's 1 plus cosine a. So I'm going to multiply this 1 plus the cosine of a, multiply the numerator by 1 plus the cosine of a. So my denominator now has two factors. The denominator has 1 plus cosine a times the sine of a. My numerator, so now let's multiply all of this together, and I'm going to get 1 plus cosine a plus cosine a plus cosine squared a. Bring down this plus sign, and sine a times sine a is sine squared a. Now I'm looking at this and I'm saying, oh, okay, let's do a little math here. Let's add those two together. And we know this is the same as 1. That's your Pythagorean identity. Cosine squared a plus sine squared a is 1. So I have this 1 plus 2 cosine a plus that yellow one right there, all over 1 plus cosine a times sine a. Now we know that 1 plus 1 is 2. So let's rewrite this now as 2 plus 2 cosine a over 1 plus cosine a times sine a. In my numerator, I'm going to factor a 2 out of each term. 2 times 1 plus cosine a over, maybe some of you can see where we're going with this, 1 plus cosine a times sine a. And now these cancel, and I'm left with 2 over sine a, or 2 times the cosecant of a. Now let's take a look at trying the next one. Next one, we're going to add our fractions together. But in order to do that, we have to get a common denominator. So I'm going to multiply the right side by a giant 1 that has 1 minus the cosine of b in it. One minus the cosine of b over 1 minus the cosine of b. And over here, I'm going to multiply by a giant 1 that has 1 plus the cosine of b in it. Because this is going to give me common denominator so I can add my fractions together. My numerator right here, let's change color. One plus cosine b times 1 is just 1 plus the cosine of b. Bring down this plus sign, plus 1 times 1 minus the cosine of b is just 1 minus the cosine of b. In my denominator, if I multiply these together, my denominator looks like this. 1 plus cosine b minus a cosine b minus cosine squared b. Those add to 0. So now in my denominator, still focusing in the red, the denominator, I have 1 minus cosine squared b. The numerator cleans up nicely because cosine b and negative cosine b add to 0. So that leaves me with 2 over 1 minus cosine squared b. Your denominator, that's part of your Pythagorean identity. That's the same as sine squared. So I'm going to replace this as 2 over sine squared b. And that, same as 2, I'm going to write an extra step in here, 2 times 1 over sine squared b. And we know that this has a reciprocal function of cosecant squared b. These are the types of proofs and identities that we're working up towards. These are the things by the time we're done with this chapter, we're hoping you're able to prove. We're going to do just one more. What I'd like you to do is, well, first of all, we're going to skip part D, so we'll just cross that off. I would like you to pause this after I give you some instruction. I want you to think about how you would factor your numerator and just see if you can't simplify this a little bit by factoring your numerator. Pause this and then come back and check your answers. Okay, hopefully you noticed that you can take that numerator and it's the difference of two perfect squares. So you end up with 1 minus cosine squared e and 1 plus cosine squared e. So I'm going to replace that right there with 1 minus cosine squared e and 1 plus cosine squared e. Well, there's a 1 plus cosine squared e in the denominator. Therefore, this factor and this factor cancel, and you are just left with 1 minus cosine squared e, which by the Pythagorean identity is the same as sine squared e. Hopefully you enjoyed. Oh, hang on, we got a couple things going on here in the next page too. Here are your 3 Pythagorean identities in the middle of the page. Sine squared plus cosine squared equaling 1, tangent squared plus 1 equaling secant squared, and 1 plus cotangent squared equaling cosecant squared. There are variations that we've used of this, and I'm not going to be able to fit all of these variations on this page. But if you were to subtract a sine squared from both sides, you would have cosine squared x equaling 1 minus sine squared x. Or if I subtract a cosine squared from both sides, sine squared x equals 1 minus cosine squared x. You can do the same thing with the other two. If I was to subtract a tangent squared from both sides, 1 equals secant squared x minus tangent squared x. Or if I was to subtract 1 from both sides, and we used this once today, tangent squared x equals secant squared x minus 1. Over here, if I was to subtract a cotangent from both sides, 1 equals cosecant squared x minus cotangent squared x. Or if I was to subtract 1 from both sides, the cotangent squared x equals cosecant squared x minus 1. There are also identities that we have used in the past, just really haven't named these. We know that the cosine of an angle is also equal to a negative, or cosine of a negative angle. In other words, this property can be proven by looking at your unit circle. And if I go a certain direction with theta, or with, I'm going to call it theta, if that's theta, this x coordinate right there this x coordinate is going to be the same as down here, and that's for a negative theta. This x is the same, but the y then is going to be opposite. And so the cosine of an angle is equal to the cosine of a negative angle, whereas the sine of a negative angle, so here, look at my y coordinate here, the sine of that negative angle becomes out negative y. That's going to be opposite the sine of a positive angle. So if I go with my positive theta, I have a positive y coordinate there. So those are going to be two more identities that we've actually used in the past. And here are some cofunction identities, where the sine of an angle is equal to the cosine of pi over 2 minus x. And many of you use this to memorize the unit circle. If this is my unit circle, and if this happens to be an angle right there of pi over 6, the coordinates here happen to be square root 3 over 2, comma, 1/2. Well, the sine of pi over 6, that's 1/2. That's the same value as the x coordinate up here. Oops. This is 1/2, comma, square root 3 over 2. Now this angle right here, we always called pi over 3. But another way to look at it is going to be to take pi over 2, which is right there, and come back a minus pi over 6. So this is equal to, since it's the x coordinate, that's going to be the cosine of pi over 2 minus pi over 6. It's also 1/2. So those are your cofunction identities. We could go through and give examples for the other ones, or actually prove them by using some generic angles, but we're not going to. This is where things are going to get a little bit challenging. This is our toughest chapter of the year, toughest section of the year. We want you to give your best effort. Please be seeing your teachers during office hours or drop-in times, and we wish you the best. We want to help you through this. Everybody have yourself a great day, and look for another lesson tomorrow.